Hello and welcome to Differential Equations. The goal for today is to learn basics about differential equations and also talk about some mathematical concepts which are absolutely necessary to survive the course. So, to start things off, we are going to first define differential equations, see what they represent, what they are, and then we are going to take a look at prerequisites and things you guys need. So let's start with this definition. So differential equation is the equation containing independent variable function and function derivatives, one or more. So in the language of Calculus 3, you can denote this explicitly as, let's say, t is independent variable, and I can have y, let's go with f of t, f of t, f prime of t, f double prime of t, dot dot dot, equal to 0. Or we might have a g of t over there or something like that as a driving term, but we'll see that later as we go on, because we are going to distinguish between homogeneous and non-homogeneous equations. Great. Well, that's our first step to understand what differential equation is. And now we are going to take a look at an example of differential equation, something let's say very simple, like y prime equals to 9. It's a differential equation, and to solve this differential equation, first of all, why is it a differential equation? Well, it has a derivative of a function, has another function, in this case a constant 9, but it's still 9 is a constant function. We can write this using the Leibniz notation as dy over dt equals 9. And then we can separate the variables. So dy equals 9 dt. Then we integrate both sides, and this is where some of our major prerequisites kick in. You need to know integration, because integration is backwards derivatives. If we are solving differential equations, well, differential equations have derivatives, then the opposite of derivatives is integration. You need to know integration well in order to solve these problems. So now our integral of dy is just y, and on the other side is 9t plus constant c. Now, this part here is insanely important for differential equations. Earlier, when you miss plus c, you lose a point. Now, when you miss plus c, you might lose half of your answer. So you have to be very careful not to miss plus c. Now, some of you might say, well, we did 2 integrations here. Why don't I have 2 plus c's? You technically do. You have a plus c1 on this side and then plus c2 on this side, and then you combine them together into this 1c. So technically, it's only 1c is needed. And you can put it on either side. We usually put it on the right. So, yeah. So when you take a look here, you have your ODE, ordinary differential equation. You have the solution over here. Note that solution is a function. And you have a method. Now, this method you have seen in Calc 2. I don't know if you remember it, but you have seen it in 9.3 in Calc 2. And the method is called separation of variables in this case, which is our topic in, I believe, 1.3 is separation of variables. So you have seen the whole process here. You have a differential equation of some kind. Then you pick a method that is suitable to solve the differential equation. And at the end, you arrive at the solution of the differential equation, and that solution is a function. So now this is the time to welcome you officially to differential equations, because this is how differential equations are different than all other equations you learned before. What have you learned before? You learned exponential and logarithmic and algebraic equations. You learned trig equations. You learned a whole bunch of equations. And what do they all have in common? The solution is a number. Solution is x equals to 2, y equals to 7, theta equals pi over 4. Right? Every single time, for all equations you learned so far, you had a number as the solution. Now we have functions as a solution. So the solution is all of this. Well, technically y equals as well, but as you can see, it's a function. And you can check. You know what? Let's go green on this one. You can check because your y equals 9t plus c can be differentiated into 9. Aha! So 9 equals 9. And that's correct when you plug in, right? Because this is your equation, and you need to find y prime. And when you find y prime, you plug in y prime into y prime, and you see that 9 equals 9. So the way to check your differential equation is to simply take the derivative and plug in. So technically, there are no excuses in this course. You check, it checks out, and you know you're good. You plug things in, it doesn't check out, you know it's wrong. And you can do that for the entire course. The only thing to prevent you from that is you being lazy. That's it. Or not care. That's another one, obviously, right? But you should be able to differentiate. You should be able to plug and, shovel algebra a little bit around to make sure that the equation works. I mean, solution works in your equation. So hopefully we understand now that differential equations are equations which contain a variable and independent variable, function, and its derivatives. And the whole course will be solving differential equations. Once you obtain a solution, solution will be a function, not a number. And then you can check by using that function, differentiating once or twice whatever you had, plug it back in, working out the algebra, and make sure that everything works fine. I will give you another example, something that you are going to see in chapter 2. Let's say that you have equation of form x double prime plus 4x equal to 0. Equation like this would be called second order. And it's called a second order because it has a second derivative in there. Naturally, this one would be the first order because it only has the first derivative in it. Technically, the order of the highest derivative equals the order of the differential equation. Maybe that's worth writing on a side. Highest derivative in ODE equals the order of ODE. How about that? So if you see 11th derivative, that means that your order of the differential equation is the 11th order. If you have multiple derivatives, obviously, that's why I wrote the word highest. Now, the solution for this one would be x of t equals c1 cosine 2t plus c2 sine 2t. Now you might ask, well, how do you know that? And I will just tell you that it came to me in a dream, all right? This is all chapter 2 stuff. So be patient, young Padawans, right? Let me just see. Do I need this? No. We are lost. So again, I have differential equation and I have the solution. That's it. Now, the question is this actually the solution? And again, you will check by taking derivatives. So in order to check, I need a second derivative for here, and I need the original function there. So all of this mess is going to go there. That's easy, right? But I need a second derivative for the first part. And the hope is that all of that stuff will add up to 0 at the end. So let's see. X prime of t, so this is a check. X prime is 2. Derivative cosine is negative sign. So negative 2 c1 sine 2t plus 2 c2 cosine 2t. Well, I need the second derivative, so one more. X double prime of t is another 2 pops out, so negative 4 c1 cosine 2t. Derivative of cosine is negative sign, so negative 4 c2 sine 2t. And now we plug everything in. So x double prime plus 4x equals 0. X double prime is negative 4 c1 cosine 2t minus 4 c2 sine 2t plus 4 times open parenthesis. X is all the way up there in black, right? So we have c1 cosine 2t plus c2 sine 2t. And I hope you see they all cancel. When you distribute the 4, right, they will all cancel. So everything equals to 0, 0 equals 0, and we're good to go. So yeah, welcome to differential equation, where you can check your answers. Sometimes it's going to be more annoying than others, right? But you will be able to check the problem every time. All right. Now, we already talked about the order of the differential equation, where I said that the highest derivative matches the order. So that's a cool part. The next order of business is to talk about why are differential equations such a big deal. This is a good point for you to realize that differential equations drive everything. All of your sciences, I don't care which branch you're in, all of your physics, which is basics to whatever engineering you're in, all of chemistry, all of everything is driven by differential equations. Because we only care in sciences about systems which change, which evolve. When something is stationary, when something is constant, you measure it and you're done. There is no more insight into a pi or into a speed of light or Planck's constant. That's it, right? Gravitational constant, mass of the planets, right? That's it. Once you have that number, once you measured it with whatever method, you're done. So there's really no science there. But when the things start evolving and changing, and through time, we have a tool that measures and studies that change, and that tool is called calculus. So when things start moving in space, we say velocity, right? So you have some kind of a distance, which you denote as x, and you know that at x is a distance between point A and point B. But when you start changing the position in time, so you cover some distance in time, you get velocity. So change of position in time is called velocity, and that's your derivative. And now, all of a sudden, you have your differential equation. You can understand velocity, acceleration, not just about you walking or your car, but also, the particle in a particle accelerator, which might be linear, like one in Stanford, or might be circular, like CERN, right? So the path is going to be a straight line or curved path, and so on. And we want to know how fast the objects are moving. Now, the biggest and the best feature of differential equations is that we observe a concept in our physical reality, and we translate that sentence, that English sentence that describes the situation, we translate that into mathematical sentence, which would be differential equation, and then we solve that differential equation to come up with a function. Because when we have the function, we understand the concept, and we can build and replicate and exploit it in some way. So throughout hundreds of thousands of years of human existence, we have been technologically somewhat advanced in the last 50 years, but science started about 400 years ago with calculus. So we really couldn't do anything without it, anything significant. Not that we are doing significant things as of right now, the way we are, but it's more significant than it was 50 years ago, or it was 400 years ago. It's more significant. But in comparison to how old the universe is, it's really insignificant. So we are going to now take a look at the observation, right? We are going to take an English sentence, which is very simple, and try to fit this. If you're taking notes, try to write this in one line like I am about to. We are going to take an English sentence, convert that sentence into differential equation, which is mathematical sentence, solve it, and then look at the solution and try to understand the solution. So let's go and take a look at the sentence. Sentence goes like this, and this is something you observe, which makes sense. The change in population is proportional to population. The change in population is proportional to the population. You can also say the change of population in time, but I left it out because, of course, population changes with time. It takes 9 months to cook up a baby. So you don't observe systems that are stationary. Population changes all the time, right? People die and others get born. And it has been like that forever. So the population will change in time. You can specify that in your words, but you can also leave it out. But as you do your translation, you are going to take a look at that change of population, and you're going to say change in population dp over dt. Right? That's what it is. The word is going to be equal sign, because that's what the word is translated as. And now we have the word proportional. That, I wanted to use a different color. That is going to be constant k. And finally, the last part, population. Let's use the wood paneling, I guess. It's too close to orange. Purple. Population P. So here we are observing the basic facts of life, that the larger population will change faster. So now think about it. More population, more couples, more babies. That should be common sense. Also, more population, larger density, larger earthquake, more dead, right? So population changes more if you have greater numbers. Population changes less when it changes less. We also have a current COVID situation. People are talking about 200,000 people dying in the United States. Is that terrible? Yes, it is. Question is it statistically speaking, is it significant on 300 million population where we can very quickly replenish those numbers, I think. If you research Black Plague in Europe, which killed 1/3 of the population long time ago, it took years to replace the lost population, right? 1/3 of the population lost in the United States, that means 110 million people dying, right? 110 million in comparison to 200,000, right, which are the projections. So thinking about that is something that, right, is the talk of the population. Large population, right? And all large populations in a situation like this will have large losses. That is completely natural and it's completely expected. The change in population is proportional to population. More population, more births and more deaths. Smaller population, less of everything, right? Now, we are able to understand that through the differential equation, where we write that change in population in time is equal to Kp. And there it is. So this is what we call, in our case, first order linear ODE, ordinary differential equation. Why ordinary? Because you have partial differential equations, you have systems and all of this kind of other stuff, some of which you are going to see later in the course. Not partial differential equations, but definitely systems. So now, the word linear here is another word that will be seen a lot. And that one says that the derivatives and functions are not multiplied and divided and squared and rooted and all of that kind of stuff. So, if you look at the differential equation, if I'm to put a square here, it's no longer linear. If I put a square here, it is. That's kind of harder to understand. If you multiply p prime by p, not linear. But if you multiply p prime by another function, f of x or f of t, and a constant in front, it's still linear. So it will take you some time to get used to this linearity concept in this one. But for now, it's good to know that you are not allowed to square or square root or anything like that on derivatives. You are not allowed to combine function that's unknown with the derivative of that function in terms of multiplication and division. You are not to put function composition on the derivative, so you can't have sine of p prime, right? That's also nonlinear, and so on. So there are a couple of things that you can do, but as I said, as we go along, you guys will learn what's linear and what's not linear. All right, cool. So now we have our differential equation dp over dt equals kp, and my job is to solve this. We are going to use the method from Calc 2, the same method we are going to look again into in our section 1.3 today, not today, next week. And separation of variables. So Calc 2, and yes, I spell calc with K's, deal with that. 9.3 separation of variables. So, what do? Well, you do exactly what the thing tells you to do. Put all of the variables of one kind on one side and all of the variables of the other kind on the other side of the equal sign. Separate them. So, dp divided by p is kt. That's it. That's our life. Oops. K dt. dt, much better. Now, we integrate both sides. You can put integral before or after k. K is a constant. It escapes integration. What is the integral on the left-hand side? Chat, let's go. Let's go, chat. No, the left side. Right side, yes, you're correct. Right side is exactly kt plus c. What's the left side? Okay, left side, you came very close with that ln p. ln absolute p. All right. So, guys, this is technically a solution, right? Except we can do better. We can get p alone. In this case, you will not be always able to isolate p. You know, not always, but in this case we can. So we're going to e both sides and get this p of t alone. Now, I don't need absolute values anymore for two reasons. First reason is that now that there is no ln next to it, p can be positive or negative number, right? We were forcing earlier p to be positive with absolute value because we can't take ln of a negative number. I mean, we can, but we get complex values. So we were forcing earlier p to be positive because ln of a positive number gives us a real value. But now that there is no ln, well, there is no need for absolute value. However, the other reason why we don't need absolute value now, once we take e on both sides, is, guys, we're talking about population. You never talk about negative population. It has no meaning, right? If the species of whatever is extinct, it's at 0. It cannot be at -5 units, or species, or whatever. So you can have 5 pandas, you can have 0 pandas, and you can have, that's it. You can't have negative number of pandas. So I don't know if you're on board on me with me to just let the pandas die out. I don't know. If I strike a nerve with anyone, well, any species that I don't want to procreate doesn't need to live either, right? But anyway, so we don't need absolute value anymore. We need absolute value here because of ln, but once you hit E both sides, no more need for absolute values. Now on the other side, we have E to the kt plus c. Now, I see a question. Is it okay to leave this? And the answer is no. Why is the answer no? Maybe I should wait until I'm done with the problem? Yeah, let's wait until I'm done with the problem. So now, I will answer that question. I'm going to use the formula from algebra where x to the m times x to the n is x to the m plus n, which is something you learned all the way in algebra 100 years ago. So that allows me to split this into e to the kt times e to the c. And do we all agree that these are all constants? So we say e to the c is going to be p0, also known as initial population. So now we're going to write our solution as p0 e to the kt and put the box around it. Now I can finally answer your question. Can we leave answer like this? And I said, hell no. Now, why is it no? First of all, why are we doing all of this? It was a word problem in which we were trying to find the formula and understand the world around us. Understand this dynamic of population. How does it change in time? Can you really see that from here? Can you see if I don't have disease here, if I leave it like that? Do we see that that is an exponential model? We don't. Do we see that population grows exponentially, decays exponentially? We don't see that either, right? So it's hard to observe that. We also have additional feature here, this puppy right there, called initial population. So technically, what I do is I say, here is an island that just has grass. So I'm going to bring 100 rabbits here. And I'm going to observe what happens to rabbits and grass. Or you can put cabbage, right? What happens to cabbage and rabbits in a year or in 2 years, right? You're looking at the population. But you are starting with initial population of 100 rabbits. That number 100 goes for initial population because that island did not have rabbits before. And now I'm bringing 100 rabbits. So initial population for that island is 100. Now, what are we expecting that's going to happen with the population of rabbits on the island that have no natural enemies? There are no snakes. There are no hawks and eagles. There are no, what else? What else eats rabbits? Owls eat baby rabbits. What else? Fox, right? None of that stuff is on the island. What's going to happen with rabbits? Well, that will also depend on this. We know that time is going to be 1 year of observation. So I know that. I know what he is. I know that time is 1 year. I know that P0 is 100. See that K there? What is the K now? Right, in this model, this K is going to be a constant of population growth or decay. And that constant will tell us whether the population will grow, stay the same, or die out. Because that k is going to put a couple of factors together and call it a number. You see, what happens to the yes, it's the rate of change of population. Very good. I was saving that word for later, but now that you mentioned it, I'm going to use it since you already know what it is. So that k is the rate of change of population in a sense that would population change if I drop 100 all male rabbits or all female rabbits? Doesn't matter. Will the population change? So there's nothing to kill them, but they have no means of reproduction because it's the same sex, right? So in a year, you know, you should still have the same 100 rabbits there. Now, think about this, and understand that this k is not just the predators, it's also the ratio male to female going into the island, and the amount of food, right, the resources. Because if you put 100 rabbits and you put three cabbage, that's it. I mean, most of them are going to die, right? So there is a lot of things that we can learn from thinking and observing these models. Another differential equation that I am going to quickly write and give you an example of is your projectile motion, right? The parabolic motion. If you shoot something from here, it goes parabolic and it falls there. It's going to reach y max at some time t1. It's going to be shot at t0. And you can actually compute the height at which maximum height to which this object is going to go. And you start using differential equations because you say that your acceleration is negative g. And then when you write your acceleration as a change of velocity in time, because that's what acceleration is, right? If you accelerate, you go faster. If you decelerate, which is braking, you go slower. Those are the two pedals you have on a car. By the way, if you have a car with 3 pedals, it's time to upgrade. All right, we are moving to a car with 1 pedal, with electric. And some people are still on 3 pedals. So change in velocity over time is your acceleration. And now that's negative g. When you do your separation of variables, you get your dv equal negative g dt. And now when you integrate both sides, what do you get? You get that the velocity function is negative gt plus some constant c. Call that c initial velocity. Because it is. Remember, initial is a beginning of time. Beginning of time is t equals 0. T equals 0 kills this. So at the beginning of time, velocity is c. Well, the beginning velocity is velocity 0. So your final velocity is equal to initial velocity minus gt. Hey, that's a formula you know from physics, hopefully. And now we realize that your velocity is change in height in time, which let's put negative gt plus v0, the math way. Do your separation of variables again, and integrate both sides. So what do you have? You have your y, which is the height, and function of time. Does it make sense for the height to be a function of time? Hell yes, because at this time you are this high. At this time, not you, object, unless you shoot yourself. You know, like those circus cannons? Yeah. So this one goes there. You see that? So as the time progresses, the height changes. So height is a function of time. Perfect. So now when I integrate, I get y as a function of time is negative gt squared over 2 plus v0t plus some constant c. And now you can write your equation as negative 1/2 gt squared plus v0t plus y0 is your initial constant, right? At time equals 0. These two terms go away at time t equals 0. And you see that your initial height at time 0 is initial height y0. So that's why we have c to be initial. It's not always that case, but in our first two examples it is, right? Initial population and initial height, initial velocity, right? So they were all initial there. Here's your physics formula, which you can use to compute the height of the object at any given time. You need to know how fast you shot the object, which depends on how much charge you had in the cannon, or how much velocity you used to throw a ball or a rock, what height you shot it from, right? The gravity is a constant. Just make sure you're using correct system, right? Imperial in feet per second or metric, meters per second squared, right, for acceleration. And then you have your time. So you can calculate the height of the object at all times. So there's a lot of cool things that you can do with these differential equations. And you can calculate, but technically they take care of all of the sciences. Pretty much all of the formulas that we have came from observing the nature, writing down differential equation, and then figuring out how to solve that differential equation. So another note now, going back to the question, can we just leave it like that without simplifying? Another aspect of this is you always have to simplify because you are passing this formula on to someone who needs to read it. Now, I wish that we had the curriculum where I can teach what engineers need to know and move along. I have to treat you all as mathematical researchers because that's how education is set up. So in this perfect world, right? 27 of you signed up in my class are all mathematical researchers who are developing these formulas for engineers and others to use. So the simpler the form, the easier it is for them to use it. That's one of the things, right? The same like technical drawings. There's only one way you can do a technical drawing, which is, you know, the rules and regulations that are set so everyone understands what is on that technical drawing. Nothing is left to interpretation, right? There are rules and you follow the rules. Now, you make those rules as simple as possible, which is simplifying your equation. So when I give you something like this, you immediately know, oh, g is gravity, t is time, v0 initial velocity, y0 initial height. So you immediately know what's what, and you can plug your numbers as engineer, do the calculation you need for the stuff you're building. But now you have to take off the engineering hat and put on the mathematical researcher hat, which means that you are simplifying all of your answers down to the simplest possible form. Now you are going to run into problems where you cannot separate the independent function by itself, and you will have to leave it. And we'll see many of those problems as well. So some problems you will be able to fix, some problems you will not. Now, the last thing I'm going to talk about here is the notion of the solution and looking at the equation, making sure that it makes sense with the reality. You see, earlier we talked about the population, and we came up with this exponential model. An exponential model looks really good, actually, because the population on this planet is really, for humans, is really growing very fast. And if you look at the model, you see that the model will be good locally, but really bad on the long run. So yes, it's the fact that we doubled the population on Earth since 1970s. So in 50 years, we are able to double the population, which means put more than 3.5 billion people on the planet. The planet might be able to sustain another doubling, which we might achieve maybe in 30 years now. And again, the COVID didn't do any damage to the world population, like 0.006% or something like that. So when you look at that, if you look at the data from statistical point, so when you take a look at the exponential model, you also have to think if that model is a good model. So exponential model for us, remember, we're only looking at positive numbers now, is going to go like that. You start measuring in some year, and that's going to be your initial population of the people you're bringing to the table, or rabbits. And then you say, what if I send this to infinity? If I send the time to infinity, what happens? And you quickly see from the model as well that the answer is infinity, which cannot be. You cannot have infinite population of rabbits or humans, I don't care which one, on a planet that has a finite surface area with a finite resources and finite everything. Even if we had 30 planets, right? If we are to colonize 30 planets and terraform and everything, you still cannot have this to be a working model for your population, because you cannot house infinitely many units of any species. So we know that this model is bad on the long run, but it does good job locally. So maybe this much is perfect, you know, dead on, year after year in predicting the population. And then after that time, whatever that critical time C is, after that time, the model becomes a complete garbage and right. So our job is to learn a different model called logistics model, and we'll deal with that next week to find a better model for population. Looking at this model here, perfect. It works 100% of the time on 100% of the cases for 100% of the duration of the flight. So we don't have to be concerned with that model. Can you send time to infinity here? Yeah, you can send the time to infinity, but once the object hits the ground, it's not moving anymore, so there is no reason to ask what's south of a south pole, right? Because the object is not falling anymore. And that's technically what it is. Do you have infinite falling in space? Yes, you do, and it's called the orbit. So Earth goes around the sun, right? It's infinitely falling through space, just like the moon is infinitely falling in the orbit around the Earth. So, and they're not going to do that infinitely. What, we have another 5 billion years maybe, and the planet will be gone. So that's pretty much it. So maybe we should end the class on the, on that dark note, so that we can shed some light next time and shed some light on the coursework next class, and discover more about differential equations and see. Now let's see if you guys have any questions regarding today, where we talked about what differential equations are, making sure that the solution is a function, making sure that that solution needs to be simplified as much as possible. Also keeping in mind that some functions will not be able to be simplified. Talking about the linear, nonlinear, talking about the order of the differential equation, and obviously making sure we know how to check differential equation by simply finding the derivative, plugging it back into a differential equation to make sure that it matches. So any questions, concerns, anything? About the homework, great. The homework will be on Mymathlab. Mymathlab will be, so I'm going to open up the homework as soon as I shut off the stream today. So let's say your homework will be available at 1. It will stay on and it will close on the 13th of September. New homework will be added next Wednesday, obviously, when we cover more material. As we go, homework will open on Mymathlab. And you go in, you do as much homework as you need. And to find Mymathlab, you will Google Mymathlab. And then you will use the course ID that is provided in the syllabus. The website will ask you to pay. You can buy a single semester license, multi-semester license. Again, this is only 1 semester course. So that's technically it. Before I go, I need to leave you with a list of concepts that you need from Calc 2 to survive this course. So, integration in general, I'll put basic, that's technically Calc 1. Sections 4.9, 5.2, 5.5. Those are the sections in the calculus textbook, current calculus textbook we use. So basic integral, this is your U sub. There'll be a lot of U sub in this class. You need by parts. I believe that's 7.2. You'll need partial fraction decomposition. I think it's 7.5. I'll put a question mark there. Partial fraction decomposition is necessary for our inverse Laplace transforms, and integration by parts is Laplace transforms. So both of those are in there. And you will need power series. So I'm just going to say chapter 11, because we will literally use everything from chapter 11, and then we'll do more, obviously, with it. And then partial derivatives. That's from Calc 3. If you haven't taken Calc 3, it's not a big deal. Partial derivatives are not difficult. I will ask you to look up partial derivatives on YouTube. Find a couple of lectures to learn as much as you can about partial derivatives. And stop by the office hours. I had a couple of students over the summer that jumped into my office hours and said, Professor, I never had partial derivatives before. I looked it up online. These are the problems I did, and where are my mistakes, and so on. And we went through it, right? So, you know, do as much of partial derivatives learning as you can. If you already had Calc 3, then you can relax. We're only going to use partial derivatives in 2 sections in the whole entire semester. So it's not a huge prereq. I mean, you're going to use all of this integration above much more. This class is much more Calc 2 dependent than Calc 3. There are only 2 things from Calc 3. The other one I don't even want to mention because we teach it from scratch in differential equations. So yeah, but if you learned 17.3 in Calc 3 on the conservative vector fields, we're going to have the same lecture very soon in DiffEq. It's just going to have a different title, and I will mention it. But if you know 17.3 from Calc 3, you know entire method to solve differential equations. And it was not mentioned in Calc 3 that it's actually differential equations. So that's your prep. Obviously, knowing basic derivatives and chain rule, which I used. You saw me use chain rule when I took those 2's for a cosine and sine. So this and this, that was a chain rule, basic chain rule for derivatives. So we need that. And that's it. So I'll see you in a week, because apparently we are celebrating labor by not working again this year on Monday. So I will see you Wednesday at 11. Homework will be open right now when I shut the stream down, so you can go and have fun. For homework, you must solve minimum of 5 problems. So 5 problems is a minimum that you must solve. More than that, you should do as many as you need to. So some of you can learn from 5 problems and score an A. Some of you will have to do 20 problems and still struggle for a C. So we're all different, right? So do as many as you need. Minimum is 5, but do as many as you need. And we'll go from there. See you all next Wednesday. Ciao.